So, when we think about this, we think about a boiling point actually being the temperature where the vapor pressure of the liquid is equal to the atmospheric pressure. So that explains why we get this boiling point elevation. Now, I set up my notes so that we would talk about boiling point elevation first and then talk about freezing point depression. They're actually the same phenomenon in opposite directions. In both cases, we know that the change in temperature is equal to some constant. We call this one K sub B, the molal boiling point elevation constant times the molality. When we're dealing with freezing points, we call it K sub F. And when we are looking at this, we are calculating delta T, the change in temperature. So the boiling point's going up. We calculate the change in temperature, we add that to the boiling point. Freezing points go down. We calculate the change, we subtract it from the freezing point. Because we are doing freezing point depression in lab on Monday when I will not be here, and I will not be able to lecture for 20 minutes, I'm going to skip boiling point elevation. We're going to skip a couple pages here, and we are going to 1224. We're going to do the freezing examples first so that you will be familiar with them to go into lab. So if we look on page 1224, we'll come back to the problems on 1223 a little bit later. If we look on page 1224, we look at this freezing point depression phenomenon. The change in freezing point, delta T, is K sub F times M, and M is the molality. K sub F is the molal freezing point depression constant. You can find this in your textbook on page 501, and I think I stuck it in the very last page of this chapter handout if you flip to the last page. M is the molality. So now, this is kind of a medium level problem that I started with. What is the percent concentration of an aqueous sugar solution that freezes at negative 0.55 degrees C? Well, if you go look at that chart that I've included, it has information about the constants, and it also has the normal boiling point and the normal freezing point. I would expect at this point in time, you know that water's normal freezing point is 0 Celsius and its normal boiling point is 100. I'd expect you know that. But if you don't, go look on the chart. I would not expect that you know the normal freezing and boiling point of chloroform and benzene. That's why they're on the chart. Okay, I would expect that you can read a chart, especially when it's right here in the packet. You don't even have to go look it up. So we look at this and we say, well, water, the normal freezing point or melting point is 0, and K sub F is 1.86 degrees C per molal. So this is kind of a weird unit, but it makes the units cancel, so it works. So we look there to get the information we need for this problem. So we look at this and say, what do we know? We know delta T is equal to K sub F times M. I grab my chart, I look up K sub F, 1.86 degrees C per molal. And the normal freezing point is 0. So I know that the new freezing point is negative 0.55 degrees. So I have to calculate the change in freezing point. It's equal to the freezing point of the solution. It's equal to the normal freezing point minus the freezing point of the solution. So my change in temperature is 0 degrees Celsius minus a negative 0.55 degrees Celsius. So my delta T is 0.55 degrees Celsius. Now, we're going to calculate these so that the change is always positive. Because when we plug in delta T is equal to K sub F times M, even though I know the freezing point is going down, if I stick a negative number in here, K sub F is a positive number, it means our molality will be negative. Can you have a negative concentration? That doesn't make sense, right? So we always switch, even though the change is positive, then we subtract the change from the normal freezing point to know where we're freezing. So now I know K sub F, I know delta T, so I can solve for the molality. So this is the new stuff. Delta T divided by K sub F is equal to the molality of my solution. And my delta T is 0.55 degrees Celsius divided by my K sub F, 1.86 degrees C per molal. And so that is equal to 0.30 molal. Now, this was sort of a medium level problem. In a medium level problem now, we know the molality. Now we're going to change to a different concentration. This is what we did a few pages back, right? We've been changing back and forth. This is no big deal. So we know we have 0.30 molal, and we don't know anything about how the solution was made, but I know that I have 0.30 moles of sugar for every kilogram of water. Now, I want to change that into percent. So I want to have grams of sugar per 100 grams of solution. That's the unit I want to end up with. And we can also think of percent as just parts per 100, right? Mass of the sugar divided by mass of the solution times 100. So if I have 0.3 moles of sugar, that is equal to 342.3 grams per mole. So that means that I have 100 grams of sugar with 2 sig figs. That zero is significant. The second one is not. 100 grams of sugar per kilogram of water. I know the density of water. Water is 1 gram per mole, right? So I have 100 grams of sugar for every 1,000 grams of water, because a kilogram is 1,000 grams. But I need percent. So what do I have to do now to turn my grams of water into grams of solution? Not subtract, add, right? So I'm going to add in my 100 grams of sugar. This only has 2 sig figs. I have to stop in the tens place. So I now have 100 grams of sugar divided by 1,100 grams of solution times 100 is 9.2%. So this first half of the problem was the new stuff. Rearrange the equation, find the molality. The second half was, let's go switch to another unit just because we don't want this to get boring. Right? So that was a first kind of level problem. Now let's look at a fancier problem, because this fancy problem is what you're going to do in lab next week when I'm not here. So here's the fancy. We had 3.46 grams of an unknown molecular compound. It was dissolved in 85 grams of benzene. The solution froze at 4.13 degrees C. What's the molar mass of the compound? So, molar mass is what units? Grams per mole. I know the grams of compound, but I don't know the moles. When we were dealing with Raoult's law, we used mole fraction to figure out moles of sample and then took grams per mole. Now we're going to use molality to figure out moles of sample. So we start off with the simple. Delta T is equal to K sub F times M. Now, we know that the solution froze at 4.13 degrees C. So the first thing we do is go look up on our chart the normal freezing point of benzene. And when we look on our chart, we see the normal freezing point of benzene is equal to 5.45 degrees Celsius. So delta T is my normal freezing point, 5.45 degrees C, minus 4.13 degrees C. So my delta T is 1.32 degrees Celsius. Delta T is 1.32 degrees Celsius. That's equal to the K sub F for benzene. Remember, it's for the solvent, not the solute. And K sub F for benzene from my chart is 5.07 degrees C per molal times the molality. Well, I know the delta T, I know the K sub F, I can find the molality. So 1.32 degrees C divided by 5.07 degrees C per molal is equal to the molality, and it is 0.260 molal. Okay, so we rearranged the freezing point depression equation. Now we have to figure out how to use molality to get moles of our solute. Well, I know that this means 0.260 moles of unknown are dissolved in every kilogram of benzene. Right? That's what molality means. I want to know how many moles of unknown did I have. Well, here's the unit I want right here. So I just need to get rid of kilograms of benzene. Well, 1 kilogram of benzene is 1,000 grams of benzene. And in my sample, I had 85 grams. So now I've canceled my kilograms, I've canceled my grams. Now I have the unit I want. That is the moles of the unknown. And I have 0.0221 moles of unknown. If I know the moles of unknown, and I was given information about the mass, I can find molar mass. 3.46 grams divided by 0.0221 moles is equal to 156 grams per mole. That's the molar mass of my unknown. That's one of the hardest problems you'll see, and that is what you're going to do in lab on Monday. So, on Monday, you're going to go to lab. You're going to take some cyclohexane and freeze it, and you're going to measure in lab the freezing point. Then you're going to dump some unknown non-volatile material in there. Let it dissolve in the cyclohexane, then you'll freeze it again, and it will be at a lower temperature. You'll calculate the change in temperature by subtracting your original freezing point minus your solution freezing point, and you'll get some delta T. You'll divide that by the constant for cyclohexane, and you'll get the molality. You'll use the molality and the mass of your cyclohexane to figure out the moles of your unknown, and then you will find the molar mass. That's the goal of the experiment. Now, there's a few other parts in there too, because you first have to find the K value. But Mary will work with you. There is a PowerPoint presentation. Make sure you look at that. And you can print it out